Looking up at the night sky and contemplating those countless points of light, fine as needle tips, is something humanity has done since the very beginning of our existence. From the ancients who marveled at the flickering lights in the darkness to the modern scientists of today using advanced technology to probe deep space, understanding the universe and searching for extraterrestrial life represents one of our greatest adventures. This fascination is rooted in a profound curiosity about our place among the stars and a longing to answer one of our oldest questions: are we alone? As technology allows us to peer further and deeper into the cosmos, the discovery of life, whether microbial or the possibility of intelligent civilizations, promises not only to reshape our understanding of the universe but also to redefine our perception of ourselves and our role on this grand stage called existence. Along the path from the origins of life to interstellar silence, we will unravel the Fermi paradox and the Drake equation, confronting the exploration of civilizational survival. It is a long story, but we shall start with the dreams. Before we begin, please remember to like and share. The history of life on Earth is one of the most profound mysteries in science. For billions of years, our planet was a desolate realm filled with oceans and shaped by volcanic activity. But at some moment in this ancient world, something extraordinary happened: life began. Today, scientists are still studying this turning point, tracing clues of how simple chemicals ignited a process that eventually led to the endless vitality we see before us. When we consider the origin of life, we must first ask where it actually started. There are several mainstream perspectives, each offering different conditions and pathways for the first simple organisms to take shape. Some scientists look toward the deep sea, specifically hydrothermal vents. These fissures in the seafloor release heat and chemical substances from the Earth's interior, potentially creating a perfect environment for the first life forms. These vents, often called black smokers, are rich in minerals and gases like hydrogen and sulfur. In these environments, life still flourishes today, under conditions that are extreme to us. Many suggest that early life might have been born in such places, finding refuge from the harsh environment of the young Earth's surface. Others believe life might have originated in shallow pools or ponds. In these settings, simple organic molecules like amino acids and sugars could have formed naturally, driven by the energy of sunlight. As the pond water evaporated and refilled, the concentration of these molecules might have increased, allowing them to interact in more complex ways. This hypothesis, often called the primordial soup, suggests that the first building blocks of life spontaneously gathered and eventually formed molecules capable of self-replication. Understanding how these basic components became what we know as life is the most difficult part of the puzzle. At its simplest level, life requires a few things: the ability to maintain itself, grow, and reproduce. To do this, even the most basic life forms need molecules to store information, structures to perform functions, and a way to separate themselves from their surroundings. How these components came together may lie in the concept of chemical evolution. Over millions of years, simple molecules formed on the early Earth likely underwent countless chemical reactions, gradually becoming more complex. Some of these reactions may have produced molecules capable of copying themselves, which is a key step toward life as we understand it. Complex proteins catalyze numerous biological processes around us, but we also know that certain remarkably simple molecules, called ribozymes, possess the ability to catalyze specific chemical reactions. Replication could have been one such reaction. Once molecules could replicate, they became subject to natural selection, which is the process that drives evolution. Molecules that replicated more efficiently or were more stable would gradually become more common, and these stable molecules, interacting with one another, would slowly form more complex systems. Recent research suggests that RNA, a molecule closely related to DNA, was likely one of the first molecules capable of both storing information and catalyzing chemical reactions. The ribozymes mentioned earlier are actually made entirely of RNA. The RNA world hypothesis highlights the unique nature of RNA. It can store genetic information like a gene and perform functions like a protein, making it an ideal candidate for early life. Over time, these RNA-centered systems may have evolved into more complex life forms, eventually giving rise to life based on DNA and proteins that dominates the biological world today. However, even with these clues, the spark of ignition remains puzzling. Some researchers propose that the early Earth was frequently bombarded by comets and asteroids which carried organic molecules from space. This idea, known as panspermia, suggests that the building blocks of life might have been delivered to Earth from elsewhere in the cosmos. If true, it means the starting point of life on Earth is part of a much grander cosmic story, carrying profound implications for the possibility of finding life beyond our world. Examining the origin of life on Earth is not just about understanding our own history, it also helps scientists look for life elsewhere in the universe. By studying how life began here, we gain insight into how to find it elsewhere. For example, we now know that life can survive in extreme environments, from deep-sea vents and polar glaciers to acidic lakes. Finding life in these places on Earth expands our understanding of the conditions that can support existence, even in places that seem uninhabitable at first glance. Take the moons of Jupiter and Saturn as examples. Europa is covered in a layer of ice, but beneath it may lie a vast liquid ocean. Could life reside there, perhaps in environments similar to Earth's hydrothermal vents? Similarly, Enceladus has a subsurface ocean, and plumes of water vapor erupt from its surface. These worlds, far from Earth, may possess the raw materials needed for life to form. Even Mars, though cold and dry today, was different billions of years ago. It once had liquid water and perhaps a thicker atmosphere. Although it is largely desolate now, life may have once existed on Mars or might even still hide within its underground aquifers. Exploring the beginnings of life on Earth is like piecing together a massive puzzle with fragments scattered across time and space. Every discovery brings us closer to the answer, not only regarding where we came from but also where life might be hiding in the universe. Whether life began in the deep sea or shallow pools, whether it was ignited by chemical reactions or gifted by celestial visitors, one thing is almost certain: life possesses incredible resilience and adaptability, capable of surviving in environments beyond our imagination. What does it mean to be alive? When we think of life, we often picture plants, animals, and microbes, things that grow, move, and reproduce. But when scientists try to define being alive, things get complicated. At first glance, life seems obvious: it consumes, breathes, and reacts to its environment. But what about viruses? Outside a host, they do almost none of these things, yet they can infect and replicate inside a host. Consider robots or artificial intelligence. If they begin to think and act in ways similar to humans, will they be considered alive? The question of the definition of life has troubled scientists for centuries, and the answer remains unclear. As a reference, scientists typically use several key characteristics to judge if something is living. First, all living things are made of cells, the basic unit of life. Life can be as simple as a single cell or as complex as a human being made of trillions of cells. Second, living things need to grow and develop, usually obtaining energy from their environment. For instance, plants absorb sunlight and carbon from the air to make food, while animals obtain energy by eating plants or other animals. Third is reproduction. Living things must be able to replicate themselves, either by producing offspring or dividing into multiple copies to continue their population. Finally, life reacts to its environment. Plants bend toward light, and animals avoid danger. Interacting with the environment is a crucial part of being alive. But what happens when we encounter objects that meet only some of these criteria and not all? Viruses are a classic example. They cannot grow or reproduce outside a host and must infect a living host to replicate. Therefore, many scientists do not consider viruses fully alive. Yet viruses evolve and adapt to their environment, just like living organisms. Such gray areas make a perfect definition of life difficult. Even if a working definition is agreed upon, another big question follows: does life elsewhere in the universe follow the same rules? As humanity continues to search for signs of extraterrestrial life, scientists must question their own assumptions. Imagine how different alien life might be from the life we know. Earth life is built on the chemistry of carbon, which is the skeleton of the complex molecules that make up organisms. The uniqueness of carbon lies in its ability to form a vast variety of complex structures, which is the key to biological diversity. Thus, carbon is an ideal building block for proteins, carbohydrates, and lipids, the essential substances of life as we know it. However, could life be built on non-carbon elements? Some scientists believe it is not impossible. For instance, silicon shares many chemical properties with carbon on the periodic table. Silicon is also relatively abundant, leading to the speculation of silicon-based life existing on planets with environments different from Earth. However, this idea faces challenges. In the presence of water, silicon-based molecules are generally more unstable than carbon-based ones. Given the importance of water to Earth life, some scientists remain skeptical about the possibility of silicon-based life in environments with liquid water. Speaking of this remarkable liquid, water plays an extremely critical role in sustaining life on Earth. Water is known as the universal solvent, capable of dissolving many substances and thus becoming the medium for millions of chemical reactions within cells. Water also possesses unique properties, remaining liquid over a wide temperature range and having excellent heat storage and transfer capabilities, allowing Earth life to survive in diverse climates from frozen poles to scorching deserts. Because of this, scientists believe that on other planets, water is likely just as essential for life. Nevertheless, the search for extraterrestrial life also prompts some researchers to consider the possibility of life in environments vastly different from Earth. For example, Saturn's moon Titan has lakes and rivers made of methane rather than water. Methane is liquid at temperatures far lower than water. If life exists in such an environment, its metabolic energy levels would be much lower than that of Earth life. Could there be organisms that use methane the way we use water? This idea is fascinating, and the scientific community is only beginning to study the possible forms and operations of such life. With our current scientific understanding, the question of life without carbon or water remains open. While carbon and water are ideal for the life we are familiar with, it does not mean they are the only options. Perhaps somewhere in the universe, there exists life made of entirely different materials, living in environments we can hardly imagine. To define life, scientists have proposed a set of criteria, but as mentioned, these standards are not always clear-cut or necessarily universal. The life we know follows chemical rules based on carbon and water. However, when we gaze at the stars and wonder if there is life, Elsewhere, we must keep an open mind. Other forms of life might be built on different elements, different chemistry, and different rules. The search for extraterrestrial life is not just about finding creatures like us, it is about expanding the boundaries of our knowledge regarding what life is and what it can become. Despite many speculations, the most practical path to discovering extraterrestrial life remains searching for life similar to that on Earth. After all, we only know for certain that this type of life is viable in the universe. In the search for extraterrestrial life, one core concept scientists focus on is the habitable zone. This refers to a region around a star where conditions might be just right for life to thrive, especially the kind we understand. The habitable zone is also called the Goldilocks zone. The planet here is neither too hot nor too cold, allowing liquid water to exist. Since water is vital to life on Earth, finding a planet in the habitable zone means a higher probability for life to develop. The key factor in determining whether a planet is in the habitable zone is its distance from its host star. If it is too close, the heat will evaporate any water on the surface, creating a dry and unsuitable environment. If it is too far, water will freeze, making it hard to sustain life. Earth is located in the Sun's habitable zone and has thus been able to maintain liquid water for billions of years, providing a foundation for life to flourish. The concept of the habitable zone is not limited to stars like our Sun. Stars vary in size and temperature, which determines where their habitable zone is located. Larger, hotter stars have habitable zones further out, while smaller, cooler stars have them much closer. In fact, many planets orbiting red dwarfs are now popular targets in the search for life because they might offer one of the best chances to find extraterrestrial existence. A notable example is Proxima Centauri b, which orbits the star closest to our Sun, Proxima Centauri. Located about 4.2 light-years away, Proxima Centauri is a red dwarf, so its habitable zone is much closer than the Sun's. Proxima Centauri b is situated within this range, meaning it might possess liquid water or even some form of life. However, challenges exist. Red dwarfs are known for intense stellar flares, which could strip away a planet's atmosphere, making it difficult for life to persist long-term. Currently, scientists cannot confirm if Proxima Centauri b has an atmosphere. Even if it does, whether it can support life remains a puzzle to be solved. Ultimately, the key to whether a planet is truly habitable is still its atmosphere. Even if located in the habitable zone, a planet needs an appropriate atmosphere to regulate temperature and block harmful radiation. On Earth, the atmosphere not only maintains the temperature range required for liquid water but also shields us from the Sun's more dangerous rays. Planets without an atmosphere can have day-to-night temperature differences so extreme that life cannot survive. Mars is an example. It is on the outer edge of the Sun's habitable zone, but its thin atmosphere means that its once existent surface water has mostly disappeared. When searching for planets in the habitable zone, scientists use ground and space telescopes to detect distant worlds. One of the most important tools is the Kepler Space Telescope, which discovered thousands of exoplanets, many of them within their host stars' habitable zones, providing a long list of candidates for further study. Some of these planets are close to Earth in size, raising hopes that their conditions might be similar to our blue marble. However, simply being in the habitable zone does not guarantee life. A planet's own composition, atmosphere, and geological activity also determine whether life can flourish. For instance, Earth's plate tectonics help regulate the climate and cycle essential elements. Without such activity, Earth's atmosphere and climate might not have remained stable for billions of years. Scientists also look for such geological clues when searching for habitable planets. Additionally, some moons in our solar system offer alternative paths for life to survive, even if they are not in the Sun's habitable zone. Europa and Enceladus are both ice-covered worlds, but there may be liquid oceans beneath the ice. These moons are far from the Sun, however, they are subject to tidal heating from the gravitational pull of their parent planets, keeping the subsurface oceans liquid. In these cases, the energy required to sustain life does not come from the Sun but from internal heat caused by tidal forces. Scientists are particularly excited about Europa and Enceladus because their subsurface oceans might be similar to deep-sea hydrothermal environments on Earth, where life thrives without sunlight. Therefore, while the habitable zone is an extremely valuable guide, it is not the only consideration. Life may exist in places we have not yet imagined, in environments entirely different from what we observe. As technology advances, scientists are developing new methods to study these distant worlds in higher detail. One of the most exciting developments is more powerful space telescopes that will help us analyze the composition of exoplanet atmospheres. By studying the gases in the atmosphere, scientists can look for signs of life, such as oxygen or methane, which are often associated with biological activity. The habitable zone provides a roadmap for where to look, while also urging us to move beyond familiar paradigms to consider how life adapts and flourishes in a wide variety of environments. To continually enrich our discoveries, we need ongoing investment in tools and technology. It is these tools that help astronomers reveal the secrets of the universe. The discovery of exoplanets has opened a brand new chapter in humanity's quest for extraterrestrial life. It is almost hard to believe that we only recently obtained direct evidence of the existence of planets outside our solar system. For centuries, humans only knew of the planets orbiting the Sun. The idea that other stars also had planets remained a theoretical concept for a long time. It was not until 1992 that astronomers confirmed the first exoplanets around a pulsar. Since then, thousands of exoplanets have been discovered, each providing new clues about how planetary systems form and how diverse they can be. One of the most commonly used detection methods is the transit method. It works by monitoring a star's brightness and looking for the faint dimming caused when a planet passes in front of the star. When a planet is positioned between the star and us, it blocks part of the star's light, causing a slight dimming measurable by telescopes. By observing the frequency of such dimming, scientists can calculate the planet's orbit and determine its distance from the star. Based on the degree of dimming, the planet's size can also be estimated. The transit method became extremely successful with the addition of space telescopes like Kepler. Launched in 2009, the Kepler mission was specifically designed to find Earth-like planets. It observed over 500,000 stars and discovered nearly 3,000 transiting exoplanets, including those in habitable zones with potentially suitable conditions for life. By analyzing the starlight passing through a planet's atmosphere during a transit, scientists can even gain a preliminary understanding of the atmosphere's composition, searching for water vapor, carbon dioxide, or other gases that might indicate the presence of life. Another important technique is the radial velocity method. It does not see the planet directly but instead measures the planet's gravitational influence on its host star. As a planet orbits its star, it pulls on the star, causing a slight wobble. This wobble changes the wavelength of the star's spectrum. When the star moves toward us, the light is compressed, and the spectral lines shift toward the blue end. When it moves away, the lines shift toward the red end. By measuring this displacement, astronomers can calculate the planet's mass and orbital shape. Relying on this method, the first exoplanet orbiting a Sun-like star, 51 Pegasi b, was discovered in 1995. It surprised scientists. Like Jupiter, this planet is a gas giant, yet it is so close to its parent star that its orbital period is only about 4 days, making it the classic example of a hot Jupiter. Such planets were unheard of in our solar system, forcing astronomers to rethink models of planetary system formation. Since then, the radial velocity method has continued to find more exoplanets, especially those that are larger and closer to their host stars. The transit method and radial velocity method each have their own strengths and limitations. The transit method is better at finding planets that pass directly in front of their star from our line of sight, but if the orbit is not aligned with our view, it might be missed. The radial velocity method is not affected by orbital orientation but is more sensitive to high-mass planets with strong gravitational pulls. Combining the two allows for a more complete characterization of exoplanetary properties. As technology advances, astronomers have developed more ways to discover and study exoplanets. For example, the direct imaging method involves taking a picture of the planet's faint light by blocking the star's intense glare. Since stars are far brighter than planets, this method is extremely difficult, but improvements in telescope technology have allowed a few planets far from their host stars to be photographed directly. There is also gravitational microlensing, which uses the effect of mass-bending light. When a distant star is passed by a closer star from our perspective, the gravity of the closer one magnifies the brightness of the distant star. If there is a planet around the closer star, its gravity adds a small extra magnification that can be recorded. This method is especially good at searching for planets very far from their host stars, or even rogue planets floating in interstellar space not bound to any star. Through these methods, our understanding of the incredible diversity of exoplanets continues to expand. There are gas giants like Jupiter and Saturn, and rocky planets like Earth and Mars. There are also super-Earths with sizes between Earth and Neptune. Some planets hug their host stars, orbiting in just a few days, while others have highly elliptical orbits, staying far away and only approaching the star for a short time each year. Attention is especially focused on rocky planets that might hold liquid water. After all, our ultimate goal is to find Earth-like worlds where life might exist. Since we have discovered that our best hope for finding life lies with Earth-like planets, it is worth taking a closer look at the ideal candidates we have found so far. Beyond simply being neither too hot nor too cold, these worlds must allow for the existence of liquid water, a quality that often earns them the nickname Goldilocks planets. Water is fundamental to life as we know it, making the presence of liquid water a core criterion for identifying potentially habitable worlds. For a planet to be just right, several conditions must be met. If it sits too close to its host star, the heat causes water to boil away into space. If it is too far, any water remains locked in ice. Earth sits perfectly in that temperate middle ground, where water has remained liquid for billions of years, creating an environment where life could not only emerge but flourish. Rocky planets are far more likely to have a solid surface where liquid water can pool. While gas giants may possess thick atmospheres and clouds, they lack the solid ground necessary to support life as we understand it. Super-Earths, which are larger than Earth but smaller than Neptune, could be ideal candidates if they are rocky and possess atmospheres capable of sustaining liquid water. Using space-based observatories like the Kepler and TESS missions, scientists have identified an increasing number of Goldilocks planets orbiting distant stars. One of the most famous is Kepler 452b, which orbits a star very similar to our Sun within its habitable zone. This super-Earth is significantly larger than our home planet and is likely rocky, with an orbital distance suggesting temperatures that could allow water to remain liquid, making it a primary target for further study. Even closer to us, the TRAPPIST-1 system is equally fascinating. This system features 7 Earth-sized planets orbiting a cool red dwarf, with as many as 4 potentially situated in the habitable zone where temperatures might support liquid water. Because these planets are so close to their star, they complete their orbits in just a few days, allowing for frequent and repeated observations. Although many are likely tidally locked, leading to extreme temperature differences between their permanent day and night sides, life might still find a foothold in more moderate regions if they possess atmospheres capable of efficiently transporting heat. Of course, finding a Goldilocks planet is only the beginning. The next step is determining if they can actually support life, and the key often lies in the nature of their atmospheres. A thick atmosphere helps regulate a planet's temperature, shielding it from the cold of space and the harsh radiation of its star. Earth's atmosphere, rich in oxygen with a touch of carbon dioxide, provides a greenhouse effect that keeps us warm enough for life. However, too much carbon dioxide can lead to a runaway greenhouse effect, as seen on Venus. Despite being near the edge of our Sun's habitable zone, Venus has surface temperatures high enough to melt lead because its dense, carbon dioxide-rich atmosphere traps excessive heat. This proves that even if a planet is in the right location, its atmospheric composition can decisively change its habitability. Conversely, if an atmosphere is too thin, it cannot retain heat or water. Evidence suggests that Mars once had rivers, lakes, and perhaps even oceans, but today its atmosphere is thin, its water is mostly frozen, and only traces of liquid water exist on the surface. Without a strong atmospheric shield, Mars lost much of its water to space, becoming a cold and desolate desert. Understanding the atmospheres of Goldilocks planets is essential to our evaluation of their potential habitability. Next-generation space telescopes are allowing us to analyze exoplanet atmospheres with unprecedented detail, using starlight filtered through their air to identify chemical signatures like oxygen, methane, and water vapor gases that might point toward the presence of life. However, the search for Goldilocks planets should not blind us to the possibility that life might adapt and thrive under very different conditions. While liquid water is essential for Earth-based life, organisms elsewhere might survive in environments we consider extreme. Extremophiles on Earth live in boiling hot springs, deep beneath polar ice, or under the crushing pressure of the deep sea. This suggests that even if a planet falls outside the traditional habitable zone, life might still be possible if there is some form of liquid medium, an energy source, and protection from radiation. While much of the search focuses on planets, the moons orbiting giant planets could also provide suitable environments for life. Within our own solar system, moons like Europa and Enceladus have become top targets. Although they are far from the Sun's habitable zone, they suggest that life can thrive in unexpected places. Europa has fascinated scientists for decades because evidence strongly suggests a global ocean exists beneath its icy crust, kept warm by tidal heating caused by Jupiter's massive gravity. Because Europa's orbit is slightly elliptical, it is constantly stretched and compressed as it moves toward and away from Jupiter, generating internal friction and heat. The existence of liquid water is the primary reason for the excitement surrounding Europa, as its subsurface ocean may resemble Earth's deep-sea environments, where life flourishes around hydrothermal vents without any sunlight. These vents spew heat and minerals from the planetary interior, supporting ecosystems based on chemical energy rather than light. If similar vents exist on Europa's seabed, they could provide the necessary ingredients for life. Missions like Europa Clipper are designed to fly close to the Moon, probing its ice shell and plumes of water to look for signs of hydrothermal activity or other markers of habitability. Similarly, Enceladus, a small moon of Saturn, has gained attention due to extraordinary findings by the Cassini spacecraft, which observed geysers of water vapor and ice particles erupting from fractures near its south pole. Tidal heating from Saturn likely drives this process, making Enceladus one of the most promising places to search for life in our solar system. Future missions may even sample these plumes directly to look for complex organic molecules or signs of microbial life. These moons raise an important question: if moons like Europa and Enceladus can support life, what about the moons orbiting giant exoplanets? Many discovered exoplanets are gas giants similar to Jupiter or Saturn, and it is logical to assume they possess numerous moons. Even if these gas giants are far from their stars in freezing regions, their moons could remain warm enough for liquid water through tidal heating. Just as Jupiter and Saturn's moons are needed by gravity, exomoons would experience the same stretching and friction. Even if the exoplanet itself is too cold, a moon could have a liquid ocean beneath an icy shell, which could also shield life from cosmic radiation. Furthermore, a planet's strong magnetic field might provide an additional energy source, similar to how Jupiter's magnetic field induces auroras on its moons. On Earth, life depends mostly on solar energy, but on an exomoon, life might utilize the magnetic energy of its parent planet or internal heat from tidal forces. The atmosphere remains crucial here as well. If an exomoon has a sufficient atmosphere, it can regulate temperature and block radiation. Atmospheres containing carbon dioxide or methane could produce a greenhouse effect, retaining heat and maintaining habitable surface temperatures. The role of Earth's atmosphere in maintaining a habitable climate could be replicated on a moon. The challenge lies in detecting the atmospheres of such distant moons, but advancements in telescope technology are slowly bringing us closer to this goal. Another possibility is volcanic activity. On Earth, eruptions release gases and minerals necessary for life. If an exomoon also experiences volcanism alongside water and tidal heat, it could foster a hospitable environment. Searching for exomoons is still in its early stages, but progress is being made. One promising method involves using the transit method to catch the tiny extra dip in light caused by a moon passing in front of a star. Another path is analyzing the gravitational pull a moon exerts on its planet, causing slight wobbles in the planet's orbit. As instruments become more sensitive, these subtle clues will become easier to detect. If exomoons are habitable, it would exponentially increase the number of places where life might exist. After all, in our own solar system, moons outnumber planets. While planets in the habitable zone are primary candidates, moons orbiting giant planets open another exciting possibility for life, perhaps showing us one day that life can emerge in the most unexpected corners of the universe. In the quest for extraterrestrial life, scientists often look to Earth's most extreme environments for guidance. Earth's life is incredibly diverse, including extremophiles that thrive in conditions previously thought uninhabitable: extreme heat, cold, acidity, radiation, or total darkness. Studying these organisms provides valuable clues about the possibility of life in the harsh conditions of other worlds. Extremophiles show that the adaptability of life far exceeds our past imagination. One of the most striking examples is the microbial communities near deep-sea hydrothermal vents, where superheated fluids reach temperatures that would be lethal to most life. Yet, bacteria and other simple organisms thrive there by using chemosynthesis, converting chemicals like hydrogen sulfide into energy. This discovery expanded our understanding of where life can exist, proving that as long as there is chemical energy, sunlight is not required. This supports the idea that life could exist in the subsurface oceans of moons like Europa. Other extremophiles, known as thermophils, thrive in high-temperature environments like hot springs or volcanic areas. The colorful microbial pools in Yellowstone National Park are home to organisms with proteins and enzymes that remain stable at temperatures near or above the boiling point. Their existence suggests life could survive on volcanically active or tidally heated bodies. Conversely, psychrophiles survive in extreme cold, remaining functional in sub-zero temperatures. They live in polar ice and seas by using specialized enzymes and flexible cell membranes. If we look toward frozen worlds, these cold-loving organisms tell us that as long as there is a liquid medium and energy, the cold is not an absolute barrier. Acidophiles live in extremely low pH environments, such as sulfuric springs, while halophils flourish in highly salty conditions like salt flats or hypersaline lakes. These abilities are highly relevant for planets or moons with concentrated salts, such as Mars, where seasonal flows of briny liquid have been observed. Furthermore, organisms like certain bacteria can withstand radiation doses thousands of times higher than what would kill a human, effectively repairing their own DNA. This gives us more confidence when considering alien worlds with high radiation environments. Some organisms do not even require oxygen, flourishing in anaerobic environments like deep-sea sediments. This further expands the range of environments where we can search for life, as an oxygen-rich atmosphere like Earth's is not necessarily a prerequisite. Ultimately, the extremophiles on Earth teach us that life is incredibly plastic and can persist in places we once dismissed. As our understanding of these organisms grows, so does our ability to imagine life across the cosmos. When we talk about cosmic life, we usually imagine planets orbiting stars and basking in starlight. But what if life does not need a star at all? What if it can survive in the cold and dark on worlds without a sun? This brings us to rogue planets, worlds that have been ejected from their home systems or formed without ever orbiting a star. At first glance, the lack of stellar heat and light seems like a death sentence for life. However, if we look back at the performance of extremophiles, the challenge might not be insurmountable. First, the lack of an external star does not mean there is no heat. A planet can still generate internal heat through the radioactive decay of elements, much like the geothermal energy that drives Earth's volcanoes and deep-sea vents. If a rogue planet has similar geothermal processes, it could create warm subsurface habitats where life thrives on chemical energy in total darkness. Second, the idea of a subsurface ocean beneath an icy crust is a fascinating possibility. For a rogue planet, if its internal heat is sufficient to keep an ocean liquid beneath a thick layer of ice, it could possess a stable habitat. In such an environment, life could survive entirely on internal heat and chemical energy. A third potential heat source is tidal heating itself. If a rogue planet is accompanied by a large moon, the gravitational tug-of-war between them could generate enough friction to maintain a warm interior over long periods. There is even the more imaginative possibility of life floating in the atmosphere. Microorganisms have been found high in Earth's atmosphere, drifting on currents. If some rogue planets have thick, hydrogen-rich, or methane-rich atmospheres, life might survive in temperate atmospheric layers, fueled by chemical reactions. This life would be very different from our own but is not entirely impossible. The sheer adaptability of life on Earth suggests that in extreme, lightless, or high-pressure environments, life might persist through slow metabolism and unique sensory adaptations. If life exists on rogue planets, it would prove that the conditions we consider necessary are not the only answers. Imagine a universe teeming with life, where every part of the sky hides something familiar or strange. This leads to the theory of panspermia, the idea that life might not have originated on Earth but was spread through the cosmos by comets or asteroids. Certain hardy microbes can survive the harsh environment of space, and if the seeds of life can travel from one place to another after an impact, they might take root on countless worlds. If this is true, the conditions for life might be less restrictive than we think. If the universe is a cradle for life, the first things we encounter might not be advanced civilizations, but microbes or primitive organisms. For most of Earth's history, life was dominated by single-celled organisms, with complex life arriving relatively late. Therefore, the first evidence we find might be something like bacteria, which would still answer the fundamental question of whether we are alone. Of course, it is also possible that the universe is full of advanced civilizations that simply choose to avoid us. This is the core of the zoo hypothesis, which suggests that more advanced aliens might already know of our existence but follow a principle of non-interference, observing us from a distance like humans watching animals in a nature reserve. They might be waiting for us to mature technologically or socially before making contact. If the universe is full of life, why do we still have no proof? The answer might be simple: our detection methods are not yet good enough. We currently rely on scanning for radio signals or analyzing distant atmospheres, tools that are far from perfect and might miss signals we are not looking for. Furthermore, alien life might exist on completely different chemical or temporal scales beyond our understanding. There are also direct physical barriers like distance. Even if intelligent life exists, the time required to communicate across the stars is immense. The speed of light, while fast, is a constraint on interstellar travel and communication. Let's consider another angle: even if there is no native life elsewhere, could we bring life there ourselves? As we look to the stars and dream of exploring distant worlds, the temptation of terraforming emerges, reshaping an alien environment to be more like Earth. While this concept has long been a staple of science fiction, we must ask if it is possible and if we should do it. The core of terraforming is creating the conditions that sustain life, modifying the atmosphere and temperature to support humans who need breathable air and liquid water. These conditions are not naturally present on most exoplanets. That concludes our discussion for today. I wish you all pleasant dreams and a wonderful day ahead. We will see you in the next episode.